I'm going to do 4 examples for volumes by washers. The first 3 are examples out of the book. And then what I'm going to do is I'm going to write a 4th example. And I'm going to revolve it around the x-axis, around the y-axis, around a line parallel to the x-axis, and around parallel to the line parallel to the y-axis. And we're going to do it 4 different ways, come up with 4 different volumes. So the first one, I modified one of your homework problems. So I put 27m for modified. It is the region bounded by the curve y equals the square root of x and y equals x, rotated about the x-axis. The first thing you want to always do is you want to sketch these because you're going to want to find out which is your inner radius and which is your outer radius. Okay, so the square root of x and y equals x is this region right here. I want to rotate it around the x-axis. So if I rotate it around the x-axis, I get a funny-looking Pac-Man. And the first thing I'm going to do is draw an arbitrary cross-section. When I draw my arbitrary cross-section, I am now going to figure out where my inner radius and where my outer radius lie. So what I want to do is I want to go from the center of rotation as far away and touch that outer curve and figure what that is. So the outer curve is my big R, and that is the square root of x. Okay. Then I want to figure out what my inner radius is. My inner radius is the distance between my center of rotation and the first curve I hit. My inner radius is the y equals x curve. Then I can write my integral, anti-differentiate, and evaluate. So the integral, it's pi times the integral from a to b. A is this point here, and b is this point here. So that would be from 0 to 1. Again, you can figure that out by setting these equal to each other and solving. Okay, of big R squared, which is the square root of x squared minus x squared, which is my little r squared, dx. So before I anti-differentiate, I am going to simplify this. So it's pi times the integral from 0 to 1 of x minus x squared dx. Okay, now I want to anti-differentiate. So the pi comes along for the ride. The antiderivative of x is x squared. The antiderivative of x squared would be x cubed over 3. I want to evaluate this between 0 and 1. So pi, again, comes along for the ride. Evaluate it at 1. Evaluate it at 0. Take the difference in between the two. So I end up with 1 squared minus 1 cubed over 3. And in this one I'll have 0 squared minus 0 cubed over 3. This cancels. I mean, that doesn't cancel. It's 0. So I end up with 1 minus a third, which is 2/3. 2/3 times pi is 2/3 pi. And that would be, again, units cubed because it is a volume. Okay, again, quick reminder, it's the big radius squared minus the little radius squared, not the big radius minus the little radius all squared. That's where I typically see students make the issue, is they put the square on the outside and not the inside. So for the first one, we got 2/3 pi, units cubed as its volume. The second one is a modification to your homework problem 29. I want the region bounded by the curves e to the x and e to the negative x between the natural log of 2 and the natural log of 4 rotated about the x-axis. Again, first step is to draw a quick sketch of my curves. So I'm going to put the natural log of 2, I'm going to put the natural log of 4 on the x-axis. 1 is where both of these graphs cross the y-axis. My e to the x graph is going to look like this. My e to the negative x graph is going to look like this. And I want it bounded by the natural log of 2 and the natural log of 4. So what I do is I draw my curves. I erase the parts that are not in my region. And then I am going to revolve that figure around the x-axis. And that's going to give me something that looks like bigger to smaller. Smaller in here, bigger out here. Where I end up with that. So that is my region of my solid, what my solid is going to look like. I'm now going to draw an arbitrary cross-section. My next step is to figure out what big R is and then what little r is. So big R is the distance between the center of rotation and the farthest point that I touch, and that's my e to the x curve. My little r is from the center of rotation to the inner point, and that's e to the negative x. With those two pieces of information, I can now write my integral. My integral is pi times the integral of lower bound, what's the natural log of 2, upper bound, natural log of 4, big R squared minus little r squared and you should be able to see that if I were to square e to the x, power to a power, you multiply. That's how I got both of these. Now what I'm going to do is anti-differentiate and then evaluate. So to anti-differentiate, pi comes along for the ride. The derivative of e to the 2x is e to the 2x divided by the derivative of the inside function, because this is linear, so divided by 2. Okay, the derivative of e to the negative 2x is e to the negative 2x divided by the derivative of the inside function, which would be dividing by negative 2. Negative 2 times the negative is going to turn it into dividing by 2. Okay, and I want to evaluate this between the natural log of 2 and the natural log of 4. So to do the evaluation, what I'm going to do is evaluate at the upper limit, evaluate at the lower limit, subtract the lower from the upper. So pi comes along for the ride. Upper limit minus lower limit, evaluated, and then, so for the first one, e to the 2 times natural log of 4 over 2 minus e negative 2 natural log of 4 over 2. This is e to the 2 times natural log of 2 over 2 minus e to the negative 2 natural log of 2 over. I'm going to show you work to evaluate one of these, and I'm going to use that same process for all of them. If I have e to the 2 natural log of 4, cannot do that directly as written. Powers of logarithm properties allow me to bring this 2 up here. So that would be equal to e natural log of 4 squared. The natural log of 4 squared is e to the natural log of 16, and that would just result in a 16. So I'm going to do this process for each of these. This 2 is going to come up here. That's going to give me natural log of 16. E to the natural log of 16 is 16. 16 over 2 is 8. So pi comes along for the right. This first term here is 8. Bring the negative 2 up here. So that would be 1 over 16. E to the natural log of 1 over 16 is 1/16. And I messed up right here. These are both pluses. 1/16 divided by 2 is 1/32. Minus the quantity. The 2 comes up here. That gives me the natural log of 4. E to the natural log of 4 is 4. 4 over 2 is 2. E to the negative 2. Negative 2 natural log of 2, that would be the natural log of 1/4. E to the natural log of 1/4 is 1/4. 1/4 divided by 2 is 1/8. Again, pi comes along for the right. 8 minus 2 is 6, plus 1/32, minus 1/8. Lowest common denominator are 30 seconds, so this is 192 30 seconds. I'm going to go this way. So I have pi times 192 30 seconds plus 1/32 minus 4/32. And the final answer would be 193 minus 4, which is 189. 30 seconds, pi. So again, remember you have to use your properties of logarithms. Show all your work. I do need to see each of these intermediate steps. I do not have a problem with you multiplying 6 times 32 in a calculator to get the 192. But in order, I need to see every step. If I tell you to evaluate it, I need to see every step that you're using for your evaluation process. Again, there may be some of these problems that I tell you just to write an integral that can be used to find the volume, and you would stop at this step. I could tell you to write and integrate, but do not evaluate, and you would stop at the second step. But if I tell you to evaluate, you would go all the way down showing all work to give me an exact answer. So the final example of this first group is directly out of your book. It is the region bounded by the curves y equals x plus 2, x equals 0, x equals 4, rotated about the x-axis. First step is to sketch the curves. So the first curve is y equals x. That would give me, and I'm only going to do it in the region that they want it. That's my y equals x line. Then it says y equals x plus 2. That would be that curve. X equals 0, x equals 4. So this is the region that I am going to revolve about the x-axis. If I revolve it around the x-axis, I'm going to get this region here. So the solid I get has a hole here, and it goes all the way around like this. So there's my solid. We should be able to see that it's a washer. My first step is to draw an arbitrary cross-section after I do my curve. I need to figure out my big R. My big R is the distance from the center to the last place it touches. Well, the distance from the x-axis to a curve is the equation of the curve. So my big R is equal to x plus 2. My little r is the distance from the center to the first curve it touches. The distance from an axis to the curve is the equation for the curve. I am going to actually square both of these now. The square of that is x squared plus 4x plus 4. The square of that is x squared. I can now write my integral. My integral is pi, lower limit of 0, upper limit of 4 of big R squared minus little r squared dx. Notice x squared and x squared give me the 0 when I subtract that one. So I end up with the integral of 4x plus 4 dx times pi. I'm going to anti-differentiate and evaluate. Antiderivative, pi comes along for the ride. Antiderivative of 4x is 4x squared divided by 2, which would be 2x squared. Antiderivative of 4 is 4x, evaluated between 0 and 4. So to evaluate, it's pi times the quantity of the upper limit minus the lower limit. Upper limit is 2 times 4 squared plus 4 times 4. Lower limit would be 2 times 0 squared plus 4 times 0. The right-hand evaluates to 0. So that gives me 16 times 2 is 32, plus 16. Final answer is 48 pi units cubed would be the volume of that region. So I'm going to erase the board, and again I'm going to write one problem that we're going to rotate it in 4 different ways and come up with 4 different answers. For the final group of examples, I'm going to take the curve, the region bounded by the curves, the cube root of x, and y equals x over 4. I'm going to rotate it about the x-axis, the y-axis, x equals -1 and y equals -2, and find their respective volumes by using the washer method. So the region of interest is this right here. And so the first one I want to do is I want to revolve it around the x-axis. So if I revolve it around the x-axis, I would get that shape. Find my cross section. It's right there. So I need to find my outer radius, my inner radius. So my outer radius is the distance from the center to the curve. From the x-axis to the curve is just the function, which is the cube root of x, which I'm going to write as x to the 1/3. My inner radius is the distance from the center to the inner curve, which is x over 4. So my integral, here I'm going between 0 and 8. So pi integral from 0 to 8 of x to the 1/3 squared would be x to the 2/3. That one squared would be x squared over 16 dx. Okay. For these, I'm just going to write the integrals. I'm going to evaluate them. I'm going to anti-differentiate, but I'm not going to evaluate, just so we can get through these. Okay, so I'm going to have pi times, add 1 to the exponent, which would be 5/3, divide by the new exponent. Dividing by 5/3 is the same thing as multiplying by 3/5. Add 1 to the exponent, divide by the new exponent. 16 times 3 is 48. I'm going to evaluate that between 0 and 8. Okay, the next one, what I'm going to do is revolve this same original curve about the y-axis. So this is my cross sections. So I'm going to draw an arbitrary cross section. Notice this time I'm making my slice here, so I'm going to have to go between 0 and 2 on y, which means both of these equations have to be written with x equals. So this one is going to be x is equal to y cubed. This one is x is equal to 4y. So I now need to figure out which one is my outer radius and which one is my inner radius. Well, the outer radius is the distance between the center and the farthest curve I touch. And that's the linear equation, which would be 4y. My inner radius is the distance from the center to the first curve I touch, which is the y cubed. So now I need to write my integral. My integral is going to be pi times lower limit. Now because I'm summing in terms of y, it would be from 0 to 2. Big R squared minus little r squared dy. Anti-differentiate. So I have pi divide by the new exponent, add 1 to the exponent, divide by the new exponent, evaluated between 0 and 8. And again, this one I'd have as a calculator problem if I wanted to evaluate, but I still would need to see each step where you're plugging the numbers in. More than likely, a problem like this, if I had you do all 4 of them, I'd have you write the 4 different integrals out. My next one, I'm going to rotate around the line x equals -1. So what I'm going to do is I'm going to clean up my original curve. So if my original region, 8, 2, was this region, I'm now going to rotate it across the line x equals -1. So where students make the issue is when they do the revolution, a lot of students will start here at the -1. No, I need to skip an entire 1 between there and there. So I'm now going to get that region when I rotate it. Next thing I want to do is draw my arbitrary cross section. And now figure out what my big R and little r values are. So the r's distances are from the center of rotation to the curves. Well, the big R is center of rotation to the outer curve. Well, the distance from the x-axis to the outer curve is the cube root of x plus 1. Okay, this is the cube root of x for the distance between the for x-axis and the curve, plus 1 because of this gap right here. So r is equal to x to the 1/3 plus 1. That's my big R. My little r is the distance between the center of rotation and the inner curve. Again, this distance is 1. This distance is x over 4, so it would be x over 4 plus 1. Okay, I'm now going to write the integral. I'm going to erase some of this stuff over here so I can write the integrals over here. So first thing I'm going to want to do is square both of those because my integral involves the big radius squared and the little radius squared. A binomial squared is a trinomial. So I'd end up with x to the 2/3 minus 2x to the third. Plus 2x to the third plus 1. That's my big R squared. Minus x squared over 16. 2 times the product would be 1/2 x plus 1 dx integral 0 to 8 and a pi on the outside. Okay, there are no like terms except for this one right here, and 1 minus 1 is 0. So a little bit of simplification I can do. Pi from 0 to 8. That's less than 1, so that's a squared. So I'm going to write negative x squared over 16. So that term's gone. These two terms are gone. That's still less than an x, so I'm going to write minus 1/2 x. Then x to the 2/3 plus x to the 1/3 dx. So all I did is I wrote it in quasi-standard form, descending exponents. So the anti-differentiation step, add 1 to the exponent, divide by the new exponent would be 48 with a minus sign. Add 1 to the exponent, divide by the new exponent, 1/2 divided by 2 is 1/4 with a minus sign. Add 1 to the exponent, which is 5/3. Dividing by 5/3, same thing as multiplying by 3/5 with a plus sign. Add 1 to the exponent, which would be 4/3. Dividing by 4/3 is the same thing as multiplying by 3/4, which would give me 6 over 4 or 3 over 2 with a plus sign. And that would be evaluated between 0 and 8. So that is it anti-differentiated. Now all we would have to do is evaluate it. Okay, so remember, if you're rotating around a line that's not the axis, the distance between the center of rotation and your curve needs to take into account the gap that you create when you're doing the revolution. The last one we're going to write up is revolving this same solid around the line y equals -2. So again, because I'm revolving around a line parallel to the y-axis, the equations I am going to deal with have to have x in terms of y, so I can solve it. So that's why I left those up there. So again, my first region goes out to 8. That's my original region. 2. So that's the region I'm revolving. I'm now revolving it along the line y equals -2. So before I start drawing my other figure, I need to go, since this gap of 2 here, I have to have a gap of 2 here. And that would be my solid of revolution. So next thing I need to do is I need to figure out my r's. Big R and little r. We're going to calculate their squares in a minute. So I need to draw an arbitrary slice. From that arbitrary slice, I need to figure out my big R and my little r. Well, the big R is the distance between the center and the outer curve. Well, the distance between the center and the y-axis is 2, and the distance between the y-axis and the curve is the equation for the curve, which is my linear equation. So it would be 2 plus my linear equation. My little r is the distance from the center of rotation to the inner curve. The distance from the center to the y-axis is 2. The distance from the y-axis to the inner curve is my cubed curve. So it would be 2 plus y cubed. And for my integral, I want both of these squared. So big R squared is first term squared. 2 times the product. 2 times 2 is 4, times x over 4 would just be x, plus last term squared. Little r squared is first term squared. That's not x over 4. I should have made that a 4y. So this is 4y plus 2. So this one's going to be a little different. It's first term squared. 2 times the product. 2 times 4y is 8y times 2 would be 16y. Plus last term squared. One would be y to the 6th plus 4y cubed plus 4. Notice I'm going to take big R squared minus little r squared. So I'm going to have a 4 minus a 4. So I'm going to have 4 minus 4. And you're going to see that those go away. And again, now my limits are from first slice, which would be here, to the thickest slice, which would be here. So it's 0 to 2 of big R squared minus little r squared dy. That's gone, and that's gone. So I'm now going to anti-differentiate. Add 1 to the exponent, divide by the new exponent, so I'd get 16 thirds y cubed. Y squared, 16 divided by 2 is 8. Minus 1/7 y to the 7th. Y to the 4th divided by 4, so that'd be minus y to the 4th. Evaluated between 0 and 2. So again, if it's going to have messy evaluations, more than likely I'm going to tell you to anti-differentiate but do not evaluate. You just need to get in the process. The biggest thing is you need to be able to write the integrals that you could use to calculate these volumes. So that's the end of section 6.3. Our last section for the week will be section 6.4.